So let's now go ahead and turn our attention to the next part of this case study, and we're going to dive a little deeper into what we actually did. And this was actually work I did a number of years ago when I was a professor at Washington University in St. Louis, and I was working in conjunction with the McDonnell Douglas Aircraft Company that was later acquired by the Boeing Company. And a lot of the technologies and patterns and frameworks we're going to talk about were actually all applied in production systems. So this will give you a good idea of the way things were and how the world has evolved over time using patterns and frameworks to help improve the way in which we build distributed real-time and embedded software. So if you look at these distributed real-time and embedded systems, they are typically characterized by a certain set of contexts. So they're usually I/O driven. Information comes in off of the sensors periodically, 20 times a second, 10 times a second, 40 times a second, and so on and so forth. Historically, these systems have been built in a very low-level way using assembly language or C or perhaps Ada. The way they're built is usually using something called cyclic executives, where you have a lot of global variables and a bunch of functions that get called periodically. And of course, these systems, because they're real-time systems, have many real-time constraints. Certain sensors have to be examined every so often and very predictably. Certain actuators have to be moved and effectors have to be enabled within a certain fixed amount of time. Otherwise, the airplane will fly out of control and do bad things. So the problem in this space, the thing that has vexed people in this area for many years, is tightly coupled components, hard to schedule, costly to evolve. So small changes in almost anything typically cause a very large amount of rework, drives the cost up, and makes it hard to field new innovations and new security patches in any reasonable amount of time. So I was actually confronted with this type of problem many years ago when I was working as a consultant at McDonnell Douglas and Boeing, when I was a professor at Washington University. And right around that same time, I was reading the POSA 1 book. I was a reviewer for the POSA 1 book. And as luck had it, I stumbled upon a pattern described in that book. And that pattern was called the publisher subscriber pattern. And as I was reading the pattern and reviewing the book, and going to these meetings with McDonnell Douglas talking about their avionics control systems issues, it became very clear to me that the publisher subscriber pattern could be exactly what we would need in order to address the challenges with trying to decouple the avionics components in the avionics mission computing system we were working on. Now, what we did was we applied the publisher subscriber pattern to help decouple producers and consumers, where the producers would periodically generate I/O that was basically driven by time. Every so often, every 20 times a second or whatnot, every 50 milliseconds, events would be generated by the hardware. And then that information was routed using the publisher subscriber pattern through the mission computer to consumers that would process the data. And this turns out to be a drop dead or a very good spot on mapping from the problem and the context onto the solution that the publisher subscriber pattern is trying to address. If you take a look at the POSA 1 book, or you read the Wikipedia link I have down here below, you'll find a diagram that looks something like the UML diagram shown in this picture. And this demonstrates the structure of the roles and relationships in the publisher subscriber pattern. So of course, we have a publisher that produces events. We have one or more subscribers that subscribe to consume the events. And the events flow from publishers to subscribers through the event channel abstraction. Now, that could be a separate process. It could be a separate thread. It could be done with multicast or broadcast. The pattern leaves it up to our imagination as implementers to decide exactly how to implement these different roles and responsibilities. But the bottom line is it helps provide very nicely decoupled communication. And as you can also see here, you can slip in some event filters to avoid having to send every event from publisher to subscriber, which is an improvement upon what you'll see if you look at the observer pattern in the Gang of Four book, which really sends every event that's notified to the subject to all the observers. Here's a more dynamic view of the publisher subscriber pattern. You can see that the subscribers register with the event channel. When the publishers produce the event flows to the channel, and then the channel pushes the event on to all the interested subscribers, potentially filtering out things that different subscribers don't care about. Well, this pattern obviously is not unrelated to the observer pattern. It's also got other characteristics about some other patterns we've talked about before, and other patterns you might find in the Gang of Four book, things like mediator and so on. But it's a pattern that's really worth understanding in its own right, because there's a whole body of middleware called pub sub middleware that implements this particular pattern. Well, as it turns out, we took the pattern description that was in the POSA 1 book that I was reviewing, and we all sat down and took a close look at this pattern. And then we went back to our domain of avionics mission computing and figured out how to map the roles and responsibilities documented in the pattern into our mission computing architecture. And this allowed us to decouple the sensor event producers, things that read the sensor data periodically, from the control system event consumers. And we did this by using anonymous pub-sub communication to publish the information in ways that didn't tightly couple the publishers and the subscribers. We used group communication where necessary to send things through broadcast or multicast. And we also, of course, made the whole thing asynchronous, so that didn't require blocking threads, which greatly cut down on the number of threads we needed in our system, which in turn improved the time and space relationships and resource utilization. If you take a look at this paper at the link at the bottom of the page, you can read a lot more about how we actually went ahead and implemented this particular project. Well, what was interesting was that the pattern got us off on the right foot. It helped us understand what the key issues were, what the key abstractions were in the architecture, but it left a lot of things up to our implementation decision-making. We had to figure out the event notification model. For example, do we push both the data and we push sort of the metadata or the events and also the payload data? You know, is the control data going with the payload data? Are they all pushed? Do we push the control data? Do we pull the payload data? And we ended up settling on kind of a hybrid architecture that pushed control data and then pulled the payload data. And that made sense for our particular use case. But the point was that the pattern got us down the road, but it didn't answer all the issues we had to deal with at the implementation level. Another thing to note was that the POSA 1 book talked about the pattern more kind of from an enterprise computing point of view. And we were dealing with real-time embedded systems. In fact, as we'll see shortly, distributed real-time and embedded systems. So that required us to think more about scheduling and synchronization strategies. And so we came up with some really clever techniques that used priority-based dispatching, used first in, first out, or FIFO dispatching in order to be able to preserve the real-time properties and real-time deadlines in our system. And once again, the pattern in the POSA 1 book kind of got us started, but we had to think through a lot of the tricky implementation issues to make things work. And then we also had to go and implement some very interesting event dependency management capabilities using advanced and optimized event filtering and correlation mechanisms. And you can read more about these in the paper that are linked at the bottom of this slide. So the point of all this is that we learned a lot of great things by reading the pattern, but it was more than just the pattern that helped us succeed. We also had to build technology and kind of refine the way in which we were doing things. Well, as luck would have it, we were successful with our initial prototype. We were actually able to test fly an airplane based on the publisher-subscriber pattern implementation of or refactoring of the avionics mission computing system. But of course, as luck would have it, as soon as we were successful with the prototype, then people decided, that's great, let's add a bunch more requirements. So what happened next was people said, let's go ahead and add all the functionality, not just the ones we'd stripped down for the prototype. And before you know it, we had a new set of problems. And the new set of problems we were dealing with was the fact that all of a sudden we had to have a lot more functionality that then could fit into the time and space resources in a single board computer, which is what we started out with. So we kind of thought about this for a bit and we said, what do we need to do here? What's the context? Well, it turns out we actually had to have multiple processor boards and we needed to have communication between publishers and subscribers on the different processor boards. And that required us to be able to do inter-process communication with stringent quality of service requirements. We needed to keep the latency low. We needed to keep the jitter low. We wanted to make things predictable. We wanted to make things secure. We wanted to make things work correctly over the types of real-time event buses that were available in our mission computing backplane. Well, if you've ever done much programming at this level, you know that it's tricky to try to write networked code that will be not fraught with low-level message passing details and memory management issues and demultiplexing and protocol processing and the fact that you've got different byte orders in the hardware and just all the inherent complexities of trying to build a network system. So what do you do to try to detangle the Gordian knot of complexity in this space? Well, what we ended up doing, once again, was looking in the POSA 1 book, and we applied something called the broker pattern. And the broker pattern is a pattern that's we used it to isolate applications, the clients and the server code from the underlying infrastructure needed to communicate messages from one processor to another across a high-speed backplane. And so what broker allowed us to do was it allowed us to connect client code that looked like they were making object calls or method invocations on remote objects without actually having to worry about all the low-level details of passing messages back and forth between computers. And so it encapsulated all the low-level details. If you're familiar with the concept of an object request broker, this is exactly what we implemented back in the day using this pattern to guide us. An object request broker, of course, is an instantiation of the broker pattern. And you have a client that makes method calls through proxies. The proxies flow through a broker, and then the broker arranges to route the calls to the appropriate object. And the messages are turned from kind of bytes back into method calls by something called an adapter. So right off the bat, you also get the sense that there's more than just the broker pattern going on here. There's many other patterns, in fact, as we'll see in a minute, involved in doing this. So we went off and implemented the broker pattern, and we did it using a standard-based approach called the Common Object Request Broker Architecture, which was all the rage back in those days. And that allowed us to be able to decouple from the programming language details, the operating system details, the network protocol details, and the hardware details. So we could write code that would work with C++ or C or Ada or later with real-time Java and run it on top of VxWorks and real-time Linux and Solaris and all kinds of different things. If you want to learn more about this, take a look at the link below, and it kind of talks about what we did in that space. Once again, the pattern got us quite a long way to the solution, but there were still a bunch of niggling issues that weren't addressed in the broker pattern as described in the POSA 1 book. In particular, all the issues related to real-time end-to-end quality of service, such as bounding latency, bounding jitter, preserving priorities from client to server. And we had to figure those things out. And those were documented in pattern form and in other ways over many decades. There were other illities that were important also: dependability, security, scalability, and so on. And we'll talk later when we get into the pattern language discussion about different aspects of the pattern languages for handling these kinds of illities. Now, what's interesting about this is once we got to the point of having ourselves the broker pattern, we realized that broker and publisher subscriber were really helpful for getting us to the architectural insights, but there was more to it than just that. So we actually had to think deeper about other patterns that were necessary in order to succeed. And one of the key things that is underscored by this insight is the fact that patterns aren't islands. We had to adopt other things in order to be successful. So what we're going to talk about next are some other patterns that we used in order to implement the broker and publisher subscriber patterns.